Hey everybody, this is Nicholas. I'm here to show you how to do problem 3.51 in your textbook. For those of you who haven't looked at the problem yet, basically we have a mass and it's supported by a rope, that's AB. It's also supported by a spring, that's BC. So the problem tells us a couple things. It gives us the mass um, of what we're suspending, so that's 50 kilograms. It gives us the distance between A and B, which is half a meter, gives us distance between B and C. Now this is the spring, so it gives us the distance of the spring when it's stretched and when it's unstretched. And it also gives us the distance between A and C. Alright. The point of the problem is to figure out K, the spring constant. So to figure out K, we're going to need to figure out what the force in the spring is, but in order to figure out the spring force, we're going to have to figure out most of the forces in the system. So step one, we're looking for the forces, so we may as well create a free body diagram, because that's going to be a really good visual aid in figuring out the forces, okay? So let's see. Go ahead and draw a box here, and this is going to represent our mass. We'll just call it M. So we have gravity in the system, so this mass has a weight. Call it W. And as always, this mass times gravity is going to give us the magnitude of our weight force. All right, now we have a spring. Since we're stretching the spring, we're making it longer. It's going to try to pull the spring back to its original length. So we're going to have a spring force acting this direction. Call that Fs. And it is acting at some angle. We don't know this angle yet, but we'll just put a placeholder variable. We'll just call it phi for now. We're going to go ahead and find that later. And then we also have the rope. So ropes always act in tension. So that's this direction. So the rope is going to be pulling the mass upwards also. So we'll call this T. And we'll say that this guy is acting at an angle theta. All right. So if we want to figure out the magnitudes of all the forces, we're going to need to break them up into their components. But to do this, we're going to have to figure out the angles first in order to figure out the components of each of these forces. That's going to be step 2. We're going to need to determine the angles, all right? So I have this triangle drawn here, and it's going to be useful in helping us figure out the angles. So we have all the lengths. Those were given to us in the problem. So you guys might remember from previous geometry or trigonometry classes, the law of cosines and the law of sines. I have them written down here for you guys if you've forgotten them. Over on the left, we have the law of cosines because we have a cosine term here. And on the right, we have the sine terms. So the way the law of sines work is you look at the angle. So for example, alpha here, or the top is the generic form, the sine alpha divided by A equals sine beta over B. But I wrote it down in terms of our triangle down here. So you're always taking the ratio between the sine of an angle, so theta, divided by the length of the side facing the angle, so that's BC. And then sine of beta, that's this guy, divided by the side that's facing it, that's AC, this value. Okay? And then law of cosines, whatever term is over here on the left that's being squared, that's what angle we want over here. So this Greek letter is gamma. That's just generically what it's called in the law of cosines formula. But in this case, we want to plug in beta here because we want to figure out what angle beta is first. I guess if you wanted to, you could just use law of cosines twice and figure out what theta and phi are, but this is the way I'm approaching it. So basically, gamma, or beta, is equal to the inverse cosine. Let's plug in some values. Okay, a squared here. So it doesn't matter if side AB or side BC is A. We'll just use AB here. So we'll say AB squared, and then whichever one A isn't, B has to be that. So we got BC. And then C. So C is the side that's facing our angle. So that's side AC. we're going to take all of that and we're going to divide it by 2 times AB times BC. And we're going to take the inverse cosine of all of that. Okay? So I'm not going to plug in the values here. I went ahead and did that previously. So on the next page, I'm going to give you what all the angles work out to be. So once we find beta, it's really easy to use the law of sines to figure out theta and phi quickly. So that's why I went ahead and used the law of cosines only once, because it's a lot to plug into. So this is my approach. All right, awesome. So now we have our angles. So now we can go ahead and figure out the magnitude of our forces. So the way we're going to do that is we're just going to look at our equilibrium equations. So basically sum of the forces in the x, sum of the forces in the y's. So let me go ahead and write that out. Sum of the forces in the x, and we're at equilibrium, so that means this is equal to 0. What forces do we have acting? We had some tension. If you flip back to the free body diagram, I'll just redraw it right here. We had some weight. We had the spring. We had tension. I'm going to say that we have x positive to the right, y positive up. All right. Forces in the x, we got Fs. That's positive. We have some angle here. I said that angle was phi. So looking for this component of it here. That's the cosine term. Tension's in the opposite direction. Also looking at its cosine component. Alright, so let's go ahead. We're going to solve for tension up here. That we can plug it into the sum of the forces in the y equation, okay? So we have tension equal to Fs cosine phi divided by cosine theta. Awesome. Now we're going to look at the forces in the y. Alright, now here, again, we have the spring force. And since we already use its cosine component, now we're looking at its sine component. Tension is acting upward also, another sine component. That one is sine of theta. Alright, and mg is acting down. And this is also in equilibrium, so we have 0. Okay, so let's go ahead and substitute in what tension equals. Oops. Copy that down wrong. So now, just isolating spring force, we can figure out its value. So basically what I did is I factored Fs out over here. Let me just Fs out. And divided by what was multiplying the coefficients of Fs, and divided mg by that, and then I end up getting that Fs is about 377 newtons, and T is equal to 345 newtons. So I got Fs by solving that last equation, then I got T just plugging it back up in the other equation. Now we're looking for spring force, or the spring constant, so we know that it's equal to, spring force is equal to spring constant times change in length. Go ahead and isolate K. We know what the spring force is now. From the problem statement, we know its stretched length is 0.45 meters. Unstretched, it's 0.40 meters. Solving for this, we get K is equal to, one second, let me pull up my notes. K is equal to about 705.55 newtons per meter, and if you round, that's about 7560 newtons per meter. And that's the answer to the problem. All right, thanks, and I'll post some more videos soon.